You've heard of scalars and vectors, but have you heard about pseudovectors and pseudoscalars? Welcome back, everyone. Today, we'll explore how operators are classified based on their commutator relations. In question 6.9, we are tasked with two parts. In part A, under parity, a true scalar operator does not change. So the transformation on a scalar operator leads to a scalar operator unchanged, whereas a pseudoscalar changes sign. Show therefore that the commutator of parity operator and a true scalar equals 0 for the true scalar, whereas the curly brackets with the operator and a scalar operator equals 0 for a pseudoscalar. This, by the way, is called the anti-commutator. Okay, not to be confused with Poisson brackets from classical mechanics. In part B, we're tasked with doing a very similar thing, except for with true vectors and pseudovectors, stating that true vectors change sign and pseudovectors do not. Therefore, curly brackets equals 0 and commutator brackets equals 0 for pseudovectors. Pretty cool. A lot of new things. But why do we care about these classifications? Well, understanding the behavior of pseudoscalars and pseudovectors under parity transformations is crucial in quantum mechanics because it reveals fundamental symmetries and interactions with physical systems. These properties help physicists predict particle behaviors, understand forces, and develop advanced technologies by providing insights into deeper structure and rules governing the quantum realm. Okay, cool. A bunch of fancy words by a lot of authors. But here's a challenge. Can you name one of each quantity of these classifications? For scalars, we think of things like temperature or mass. But what about the pseudoscalars, right? Those are kind of new. And for true vectors, we've seen things like velocity and force. But what about the pseudovectors? I'm sure you know quite a few of the pseudovectors, but the pseudoscalars might be new, right? So before we begin, as a reminder, there's a free companion PDF to help you follow along, although this problem will be pretty quick and painless. Access it using the link below. Let's dive in. Alright, stop number one then. In part A, we are tasked with looking at two things. One, both of these cases we are tasked with applying the transformation equation, so 6.17 or 6.23, to an operator. But in this case, what we need to be aware of is that the true scalar or true quantity is in blue and the pseudo quantity is in green. And that'll hold for the next case too. But without further ado, if we look at this transformation equation, all we have to do is a couple steps of algebra, which I overextended because it's good to see everything at least once. Here we go. All you have to do is multiply the left-hand side by the parity operator to both sides, and you see what we have read here acting on the statement above. Easy enough. Then we see that it settles in. Everything is just compact, and by compact I mean applied to one another. No big changes yet. But what we see is the associativity where instead of grouping red on this parentheses, we can look at the parentheses right before F. Okay, so you see we successfully put the parity operator on both sides. Thus, now we need to evaluate what's in these parentheses, which if you remember the properties of the parity operator, won't be too bad. Point of notice though, be very careful with this symbol here, because the next step will use the definition of the parity operator and two of the famous types of operators that we've come to know and love. So the dagger in the last slide was great, but now in order to actually evaluate this product here, we have to use the fact that a parity operator is both Hermitian, so it is its own adjoint, and it's unitary, so it is its own inverse. Therefore, here we see that the inverse is equal to the dagger. Cool. So we put the inverse in now, which is stated in equation 6.16. And as you might imagine, we get the identity after the operator and its inverse are multiplied. So that's very nice to see. And of course, anything multiplied by the identity, by definition, gives a thing back. So we just left with f hat pi hat equals pi hat f hat. And then this side, we just have the negative. Of course, that pesky negative. But what we see here is that if we minus this f pi hat over, we get something equal to 0. If we add this over to the left-hand side, we get something equals 0. Of course, if we factor out a -1 and divide it to reorder these things, or to switch the order in this case, switch the order in this case, both are fine. We see that we have the left-hand side of a commutator and the left-hand side of an anti-commutator. Okay? And this is just a pure definitional understanding. AB minus BA, seen that before. This one probably you haven't, at least not in the curly brackets, but we have AB plus BA. Okay, cool. We like that. So note that the pseudo is classified based on this, and the true is classified based on this. Very cool. Yeah, that's pretty much it for the scalars. So we've reached our checkpoint. The vectors are going to take a little bit of the same approach, but we're not going to put all the steps in, just too much. Let's see what they do. Again, with this stop number 2, we're using the true vector is in blue and the pseudo vector is in green. So by applying the same route of equations, thanks to equation 6.17, what we show here is that apply the parity to both sides, use the fact that the adjoint is the inverse again, we get the identity, cool, push it over to the other side to where we get a side equal to 0, and we see that now the vector is transformed with the anti-commutator, and the pseudo vector has a normal commutator. So that switches what we saw with the scalars, and it's very odd. So again, parity tells us that, when we see something, either they're going to commute or not commute, anti-commutator, commutator, but it's very weird to see how these classified, but it kind of makes sense, because what does it mean for a mass to be inverted, right? That doesn't make sense in this case of a true scalar. So in that case, we see that that leads to a commutator relation because they do commute. But in the vector, just like the position vector, we saw that it inverts it in all space, so it makes sense that you have an anti-commutator because you have to add that to the other side. So all of these things are starting to make sense. It's just a weird classification, and we couple this classification style with one from the angular momentum with rotations, and we'll see that shortly. That being said, this problem is now successfully done. It didn't take long at all, but be aware that this is part of a larger classification scheme. So let's take a look at that real quick. So in this book and in several others, a lot of things are classified in something like this table. This is table 6.1, I believe. And Griffiths and Schroeder put in there that operators are classified as vectors and scalars based on their commutation relations with L. Okay, so let's take a look at that. What we see is that we have a vector, and they both have something here. And do you remember what this epsilon symbol was? That was the 𝐓𝐸𝐼 that we come to either love or hate. I have yet to see someone in between. And scalars have a 0 commutator. But notice what happens with the true and pseudos that we have going on here. Because although we have a true, change colors, we have a true, but that is a squiggly bracket. And then we have a true here, but that's a commutator bracket. Very odd. And then here we have the pseudo is a commutator for vectors, and a pseudo is a curly for scalars. So these two things tied together, they kind of work in hand. A little bit more about the table. They go commutations with L, which encode the transformations under a rotation, and a pseudo or true quantity is based on their commutation relation with parity, which encode how they transform under spatial inversion. So, really kind of cool construction here, but the true and pseudo is just a way to classify things. Once we get into rotations, it's going to be easy to see that both of them take the same form, but being able to classify what's pseudo and not might be helpful later. I'm thinking more of the particle physics realm, but yeah, we'll see that in due time. So, in summary, this video was not long at all. It wasn't supposed to be. I put more work in there, and as you can see, the work's in the PDF as well. But I think that it's easy to see and get lost in the symbols and definitions. So, kind of taking one thing and showing a full kind of nitty gritty, even though it's not that nitty gritty, but a full kind of set there, I found very valuable. Um, Again, this is just kind of one of those things where you're just like, okay, why am I doing this exercise? However, if Griffiths has taught us anything going through 1.5 books so far, is that these results end up coming up in something later. So it's worth understanding and keeping yourself aware of the classification schemes. So that's that for this question. A massive thank you to our patrons for their invaluable support making all of this possible. Please consider subscribing and sharing in order to fuel this curiosity or even becoming a patron yourself. New content is posted weekly to aid you in your curious pursuits, including my random notes that I find or article summaries. Books, notes, and other reference materials are found below. If you have any questions, please feel free to reach out. Although this question wasn't too bad and pretty straightforward, you might have questions on what is its larger role in scheme and things. Totally makes sense. But as always, thank you for watching, and until next time, stay curious.